So for question 1.3, we're asked, consider the 3-qubit quantum circuit below, which we can see consists of 2 Hadamard gates and 2 CNOT gates. And we're asked, what are the real and imaginary components of the state vector? And we're given a few options as the answer, where we're seeing this plot with some associated binary number and some bars in some sort of grid. So if you're not familiar with this, we'll get to it. But before getting to the plot itself, let's first look at what is the output state corresponding to the circuit, assuming that the input state is 0, 0, 0. So let's go and draw our circuit. So we have 3 qubits, 2 Hadamard gates, 1 on qubit 0, 1 on qubit 1, and then we have CNOT gates between qubit 0 and qubit 1, and a CNOT gate between qubit 0 and qubit 2. So we have CNOT gate here, CNOT gate here, and let's just complete the circuit here. Here we go. Okay. Okay. So first, we're going to use the same convention as before. So Qiskit organizes qubits from most significant bit to least significant bit in the state vectors. And as we said, we're going to assume it's initialized at 0, 0, 0. And then we apply a Hadamard gate or 2 Hadamard gates. So this is 2 Hadamard gates in state or in qubit 0 and in qubit 1. So if we separate this, we know that on qubit 2, there's no Hadamard gate applied, so the state stays the same. And we have this tensor with 1 over root 2, 0 plus 1, which is for qubit 1. And again, tensored with 1 over root 2, 0 plus 1, which is for qubit 0. And now if we distribute our qubits here, we know that this state is equal to 1 over 2, from 1 over root 2 times 1 over root 2, and then times state 0, 0, 0, that's this, this, and this, plus 0, 0, 1, right? So this, this, and this, and then we continue with the distribution, and we get plus state 0, 1, 0, and plus state 0, 1, 1. Now, after this, we apply a CNOT gate. So let's apply a CNOT gate here between qubits 0 and 1. So what this is going to do is, when qubit 0 is in state 0, it's going to leave qubit 1 unchanged, and when qubit 0 is in state 1, it's going to flip qubit 1. So here we have this 1 half of 0, 0, 0, because qubit 0 is 0, plus 0, 1, 1, because here qubit 0 was in state 1, so we gotta flip qubit 1, plus state 0, 1, 0. Again, no change here because qubit 0 is in state 0. And then plus 0, 0, 1. And that's because qubit 0 is in state 1, so we gotta flip qubit 1. So now, as you can see, there's really no change in this state. What basically happened here was state 0, 0, 1 went into state 0, 1, 1, but then state 0, 1, 1 went into state 0, 0, 1, which it's characteristic of this type of circuit where you have two Hadamard gates followed by CNOT gate, which is fine. We just went through the math to show that this just leaves the superposition unchanged. But then after this, we apply another CNOT gate. So now we are going to apply it between qubit 0 and qubit 2. So we go through the same exercise, 1/2, and because qubit 0 is in 0 here, we leave it unchanged. And then in the next one, qubit 0 is in 1, so we're going to flip qubit 2, so 1, 1, 1, plus 1, 0, 1. Again, this state remains unchanged. And last one is 1, 0, 1. So we flipped qubit 2 because qubit 1 was state 1. All right, and rearranging this a little bit, we have 1/2. We're just gonna put this in order. So 0, 0, 0 plus 0, 1, 0 plus 1, 0, 1 plus 1, 1, 1. All right. So that's our final state. And now let's go back to the plots that we were asked to figure out this, which of these plots this state corresponds to. So what plot represents is the amplitudes or the values of what is known as the density matrix of a state. And if you're not familiar with density matrices, then let's take a look at a simple example of what a density matrix is. So just let's write down what we just said. So this plot, which is called a state city plot, is a graphical representation of a state's density matrix. So what is a density matrix? So let's start with probably the simplest example. So let's start with a 1 qubit example for the state. Let's call it psi equal to 1 over root 2, 0 plus 1. And if we represent this as a vector, as a column vector, we know that this is equal to 1 over root 2, 1, 1. So the density matrix associated with this state is equal to the outer product. So we take the ket of our state and multiply it with the bra of the same state. Now you may wonder, well, what's the point of doing this? There's really nothing I'm gaining by doing this. There's no more information, or there's nothing additional I'm learning about my state. It seems a bit redundant to do this. Well, it turns out that density matrices are a good way of representing other types of states called mixed states, in which you're not only dealing with quantum probability amplitudes, but also classical probabilities. So we're not going to go into that right now, but it's just another way of representing states. It's a more general way of representing states that allow us to include classical probabilities. So now let's remember that the bra of a state, it's given by the if we have a column vector psi, its bra corresponds to the row vector with the complex conjugate of each of its elements. So in this case, for our example, our elements are just 1 and 1, so their complex conjugates are, also 1 and 1, so there's no need to take complex conjugation there. So then if we now multiply 1 over root 2, 1, 1, times 1 over root 2 for our bra, 1, 1. If we perform matrix multiplication of this, what we get is, well, 1 over root 2 times 1 over root 2, we get 1/2. And then we have 1 times 1, and then again 1 times 1, and at the bottom 1 times 1, and 1 times 1. So it's a square matrix with all amplitudes equal to 1/2. So in general, for a 1-qubit state given by, say, psi equal to alpha 0 plus beta 1, its corresponding density matrix given by ket psi times bra psi, it's equal to alpha times alpha complex conjugate, alpha times beta complex conjugate, and here beta times alpha complex conjugate, and beta times beta complex conjugate. And if you see here, alpha times alpha complex conjugate is actually the norm of alpha squared, and same for beta, the norm of beta squared. So what this means is that the diagonal terms of this density matrix correspond to the probability amplitudes associated with each of the basis states of the superposition of our psi state. So this is only for one qubit, but this can be generalized. This can be generalized for n qubits. Now let's go back to our problem in hand. So we had state psi equal to 1/2 of 0, 0, 0 plus 0, 1, 0 plus 1, 0, 0 plus 1, 1, 1. Now, if we wanted to find the density matrix for this state, we will have to perform the Ket-Braun outer product of our state to find every component of this matrix. But an important thing that we just learned from looking at this general case for 1 qubit is that the diagonals of the matrix correspond to the probability of measuring each of the states. So when we have 3 qubits, we know that this matrix is going to be an 8 by 8 matrix, right? Because we have a 2 to the 3 number of states, which is 8. So we will have probability associated with state 0, 0, 0 of 1 over 4, because its probability amplitude is 1/2. So if we take the norm squared of 1/2, it's 1/4, right? Now associated with state 0, 0, 1, we have a probability of 0. Associated with state 0, 1, 0, we have a probability of 1 over 4. And then for state 0, 1, 1 is 0. For state 1, 0, 0 is 0. Now for state 1, 0, 1 is again 1 over 4. For state 1, 1, 0 is 0. And for state 1, 1, 1, it's 1 over 4. And obviously for this matrix, we're going to have some probability, terms in the off diagonal of the matrix associated with the products of each of the states in our superposition. But for the purpose of this problem, we can basically focus on the diagonal to see if we can figure out the solution just from looking at what we have here. So now let's go back to our Jupyter notebook and see what we have here. So here we see that if we look at this matrix, it has some probability close to a quarter, 1 over 4, associated with state 0, 0. Then another one associated with state 0, 1, 0, right? And then another one associated with state 1, 0, 1, and another one associated with state 1, 1, 1. So this seems to be the answer to this problem, because we have diagonal terms associated with the terms that we found. If we look at the next one, our state had a superposition of state 0, 1, 0, and here we see there's no probability associated with that, so this can be our answer. Same in this case, and same in the last case. Now let's go ahead and try to implement this in Qiskit to see if we can get the same result. So what we're going to do first is, as before, from Qiskit, we're going to import quantum circuit. And also from Qiskit, quantum info, we're going to import the state vector class as we did in the first problem, but also let's import the density matrix class. Let's do that. Now let's initialize our state, so let's call it psi in, for example, and state vector. And here we're going to use this method where we can say initialize my state vector using from int or from integer, where here what we pass is the integer we want to initialize our state in, so the all zero state. And since we have 3 qubits, this state vector is going to have a total of 8 components. And if we now look at this, we can see that we correctly initialize this into state 0, 0, 0. Next, we're going to define our circuit. So QC equal to quantum circuit. And we're going to have 3 qubits. Just to remind you how the circuit looks like, it's 2 Hadamard gates, 2 CNOT gates. So what we're going to do here is apply Hadamard gates on qubits 0 and 1, and CX gates from qubit 0 to qubit 1, 0 to 1, and from qubit 0 to qubit 2. Then we're going to draw our circuit. There we go. And it looks the same as what we had above. And we're going to evolve our input state. Let's now do, for example, psi out equal to psi in evolve through our quantum circuit. Let's see how this looks like. And we have 1/2 state 0, 0, 0, 0, 1, 0, 1, 0, 1, and 1, 1, 1, which, if you recall, is the same thing we derive analytically. Now, one thing we can do here is we could plot the state series city plot using the conventional way, which is by importing from, let's say, from Qiskit tools visualization, import plot state city, and we can basically just do plot state city and pass our state psi out. And here we can see that, as we expected, our output looks just like option 1, which is what we thought was our answer after deriving this analytically. Now, with the newer version of Qiskit, you really don't have to import this visualization method. Actually, if you have a state vector, in this case psi out, you can actually just do the draw method, and you can specify here city, and you would get the exact same plot without having to import this. This is something that you can still do, and you can actually, instead of passing a state vector object, you can pass a numpy array, but this just makes things significantly easier. Now, lastly, I just wanted to show that we can define a density matrix by using the density matrix class and just passing our state vector, and we can visualize that to see that, in fact, as we had shown, the diagonal of this matrix has the probability of measuring each of the states we found for the output state. Now, if you would like to learn a bit more about density matrices, I have shared a link in the description below to the Qiskit textbook chapter on this subject. Also, if you stick around for the next video, we'll go through a simpler example where we'll derive the full density matrix for that specific case.